Hello to everybody, and today we continue mini course on Paley graphs and the theory of directions by Shamil Asghari, and today it will be the second lecture as introduction to theory of direction. Okay.
Thank you. Yeah. Thank you, Elena. So I'm really excited to talk about theory of directions. This is part 2 of my mini course. So we're going to start with two fundamental definitions. Let Q be a prime power and consider a finite field FQ. We'll consider the polynomial ring FQX, polynomial ring in one variable. And we're going to define two definitions. So a definition of a fully reducible polynomial and a definition of a lacunary polynomial. So what are these? So a polynomial in one variable defined over FQ is called fully reducible if the polynomial factors into linear factors over FQ. So fully reducible means that the factorization of the polynomial is as decomposable as possible. It decomposes completely into linear factors. Of course, we know that every polynomial factors into linear factors over the algebraic closure. But the whole point of fully reducible is that it factors over the ground field, in this case, FQ. We also have another definition, which is lacunary. So a polynomial is called lacunary if, in the sequence of its coefficients, there's a long run of zeros. There's a lot of zeros. Now, this phrase, long run of zeros, is not precise, but intentionally so. It turns out that for different contexts, it means different things. But generally, you want to think of lacunary polynomials as those polynomials with sparse coefficients. So they have few, relatively speaking, few non-zero coefficients. A lot of the coefficients are zero. So now you may ask, what kind of polynomials simultaneously satisfy both conditions? They're both fully reducible and lacunary. Well, it turns out that Laszlo Radé studied these polynomials in his monograph from 1970. So polynomials that are both fully reducible and lacunary were investigated thoroughly in the monograph called lacunary polynomials over finite fields. And much of the results I'm going to mention today really originate from Radé's ideas. So let me mention two problems that Radé considers in his monograph. Problem 1 is the following. Let D be a fixed divisor of Q minus 1. Determine all polynomials of the form f of x equals to x to the power of Q minus 1 over D plus h of x, which satisfy the following three conditions. First, the polynomial is fully reducible and not divisible by x. Secondly, f of x do not have multiple roots. And the third condition says something about the sparsity of the coefficients. So this is what I call the lacunary condition. So the third condition is that the degree of h is less than or equal to q minus 1 over d squared. Notice that the degree of the polynomial f is q minus 1 over d. And here what we're saying is that after this leading term, the next biggest term has degree at most q minus 1 over d squared. So we see that there's a long run of zeros. And this is basically the lacunary condition for us. And problem 2 is the following. Determine all polynomials of the form f of x equals to x to the q plus g of x in the polynomial ring FQX, but we don't want those polynomials to live in the subring FQ adjoint x to the p, where p is the characteristic of the field. And that's because polynomials in this ring, this is rather the subring of FQX, these polynomials have the special property that their derivative is identically zero, right? Because all the monomials that appear have exponents divisible by p. So when you take the derivative is identically 0. So we want to avoid those polynomials. So we want to find all polynomials that are of the form x to the q, where q is the same q as here, fq, plus g of x, which satisfy two conditions. One is that f of x is fully reducible. And second condition is that degree of g of x is small. So it's less than or equal to half of q plus 1. So again, we think of this as the lacunary condition. It's indicating in some quantitative sense that there's a lot of zeros in the coefficients of f, because there's no monomial which have degree less than q and bigger than q plus 1 over 2. So there's a gap in the coefficients. So these are interesting problems. And they're both asking about classification. Find all polynomials over a finite field fqx that have these properties. So turns out that problem 1 is simpler to solve than problem 2. And in fact, we have a complete answer to problem 1. So Radé himself solved this problem. And here's a complete solution. Basically, if d is bigger than 2, then the only solutions to the problem is those polynomials of the form x to the power of q minus 1 over d minus alpha, where alpha is u to the power of q minus 1 over d for some non-zero element u. Now, when d is 2, there are exceptional solutions. So there are, in fact, exceptional solutions when q is 1 mod 4. And what are those extra solutions? So there are solutions that don't look like this. Well, they look pretty similar. So they look like a product of these two binomials, where b squared is 1 and gamma squared is minus 1. Now, gamma squared equals to minus 1 has a solution in the field because we're assuming that q is equal to 1 mod 4. Okay, so now for this talk, I'm going to talk mostly about problem 2. So just to remind you, this was problem 2. Problem 2 was find all polynomials of the form x to the q plus g of x, where f of x is fully reducible and degree of g of x is at most q plus 1 over 2. And the exposition that we're going to follow in our presentation is the one is going to follow the excellent article by Tamas Sonyi. Sonyi's article called Around Radé's Theorem was published in Discrete Mathematics in year 1999. So in this paper, Around Radé's Theorem, Sonyi talks about applications of Radé's ideas in the theory of directions. And it shows applications to blocking sets, applications to group theory, and even some applications to algebraic number theory. So today I'm going to mostly focus on the theory of directions, rather almost exclusively focus on the theory of directions. But notice that at this point, the problem itself is a problem about algebra. This is the interesting thing. This problem is about algebra at this point. And we're going to see how the algebra of polynomials over finite fields have interesting geometrical counterparts. So here is kind of one theorem that is really straightforward to present with complete details. And it's a really beautiful proof that gives some constraints on what the fully reducible polynomials look like. So this is the proof of this theorem, which I'm going to show in detail, is completely elementary, but it is very elegant and it's hard to think of. So you're going to see there's few tricks in the proof, but we're not going to use any fancy technology in the proof, except we're going to just take GCDs of two polynomials. We're going to take greatest common divisor of two polynomials and manipulate some derivatives. So what does this theorem say? Theorem says the following. Suppose f of x has this very special form. So we're working over a finite field with q elements, where q is some prime power, and I'm considering a polynomial of the form x to the q plus g of x, where I'm assuming that the derivative of the polynomial is not identically 0. And that means that the polynomial is not entirely made out of pth powers. In this case, I'm saying that being fully reducible for these polynomials imply that degree of g has to be at least as big as q plus 1 over 2, or, and there's this exceptional case, when g of x is minus x. Now, in this case, we know that the polynomial factors into factors into product of linear factors, because x to the q minus x over the field fq has roots at every point of the field. Like this is when q is equal to p, this is Fermat's little theorem, that x to the q minus x vanishes at every point of the finite field. So this is a very interesting result because it shows that it is impossible to have a fully reducible polynomial where the first term is x to the q and the next term here has degree less than q plus 1 over 2, unless you're in this very special case. So we're going to prove this theorem. So why is this relevant? So if you remember what problem 2 asked, it asked for classification of fully reducible polynomials of the form f of x equals to x to the q plus g of x, where the degree of g of x was at most q plus 1 over 2, right? This is because of the sparsity condition. This was the lacunary condition. But now, in view of this theorem, that means that we can focus on the equality case, right? Because here we were asked to analyze the case when the degree is at most q plus 1 over 2, but we just showed that to be fully reducible, you must be in the case when the degree of g is at least q plus 1 over 2, unless you're in this special case. But we understand this special case very well, so let's ignore that case for a moment. So of course, combining these inequalities, we get the equality case. So this theorem is very nice because it means that for problem 2, from now on, we can focus on the case degree of g is equal to q plus 1 over 2. So here I'm going to show you the proof of the theorem. First, we're going to notice that the polynomial has zero derivative, has non-zero derivative because of the assumption, which implies that g of x is not constant. Because if g of x were constant, then derivative of f of x would be identically 0. Remember, derivative of x to the q is actually 0 because q is 0 in the field. Now we're going to consider g of x plus x. That's going to be the trick. We note that f of x can be written in the following way: x to the q minus x plus g of x plus x. Now, from this equality, we can deduce that every root of f is a root of g of x plus x. Now, why is that? Because if you take any root of f of x, since f of x is fully reducible, all of its roots are in fq. So if you take any root of f of x, it's also a root of x to the q minus x, and therefore it must be the root of g of x plus x. Right, so this is because x to the q minus x, one second. Just going to share my screen again. There was a little pause. Right. So this is because x to the q minus x vanishes at every element of fq. That is, x to the q minus x is the product of x minus c as c ranges in fq. So here's going to be step 1. There's going to be 3 steps in the solution. So all the steps are going to revolve around this polynomial g of x plus x. So step 1 is that we take capital F of x to be the greatest common divisor of little f of x and x to the q minus x in the polynomial ring fqx. Since g of x plus x is f of x minus x to the q minus x, and that follows from this equality here, it means that f of x must also divide g of x plus x. because capital F of x divides each of these terms. So it must divide their difference. It must divide g of x plus x. So that is the first step. The second step is to realize that the polynomial f of x divided by capital F of x has roots precisely at the points where lowercase f of x has a multiple root. And that's because we're taking capital F to be the GCD of f of x, the greatest common divisor of f of x, and x to the q minus x. And this has all the distinct roots in fq. So when you take this quotient, you're going to pick up exactly those extra roots, the roots that appear with some multiplicity. But it's a well-known fact that the roots of the polynomial, which appear with multiplicity, is also the root of the derivative. And therefore, f of x, lowercase f of x divided by capital F of x must in fact divide the derivative of lowercase f. So that is step 2. Well, more precisely, I'll say one more thing. Now, because f of x divided by capital F of x divides lowercase f prime, now we can use the fact that little f and g are related using this formula. So when I take derivative of both sides, I see that f prime and g prime are identical to each other, so that lowercase f divided by capital F in fact divides g prime of x, because it divides f prime of x, and they're equal. So we get this condition. We get this divisibility. Notice that we have 2 divisibility conditions, right? We have one divisibility that capital F of x divides g of x plus x, and the other divisibility condition is that lowercase f divided by capital case f, this polynomial, this quotient, which in fact is a polynomial, divides g prime of x. So step 3 is just to combine these 2 divisibility conditions. So I take the divisibility condition from step 2 here, and I take the divisibility condition from step 1 here, and I combine them. How do I combine them? Well, I can just multiply these 2 terms. This means that f of x, lowercase f of x, in fact divides the product of these 2 polynomials. So it divides the product of g of x plus x and g prime of x. Okay, so now we're almost done. We do have to be careful to take into account whether each of these could ever be 0. Well, the g prime term cannot be the 0 polynomial. Why is that? Well, because g prime is equal to f prime, as we saw earlier. And we know that f prime is not 0 identically because of the hypothesis. So g prime of x is not the 0 polynomial. But there is a chance where g of x plus x, the first term, could be the 0 polynomial. But if g of x plus x is 0, then g of x is minus x. And then f of x is x to the q minus x, right? Because f of x is x to the q plus g of x, and g of x is minus x in this case. And that's the exceptional polynomial that we considered. Otherwise, if g of x is not the 0 polynomial, then we can analyze this divisibility relation once again. From this divisibility relation, I'm assuming that this is not 0, and we already know this is not 0, we can look at the degrees. Degree of f of x is q, plainly. And degree of f of x must be at most the degree of this product, which is degree of g plus degree of g prime. But degree of g prime is at most degree of g minus 1. So it follows that the sum is at most degree of g plus degree of g minus 1, or equivalently 2 times the degree of g minus 1. And if you just look at what we proved, it follows that degree of g is bigger than or equal to q plus 1 over 2. And that is the proof of the theorem. That was the conclusion we wanted to reach. Just to remind you, that was the theorem that we wanted to prove. That if you have a fully reducible polynomial of this type, then under this condition that the derivative is not 0, then either the polynomials of the form x to the q minus x, which is very special, or degree of g is bounded below by q plus 1 over 2. And that's exactly what we proved. Moving on. I'm going to tell you a little bit about what Reday proved about problem 2. So when Q is equal to P prime, the prime case, it turns out that the answer to problem 2 can be described as follows. So suppose that you have a polynomial x to the p plus g of x in fpx, where the degree of g of x is exactly equal to p plus 1 over 2. So this should be p plus 1 over 2 instead of q plus 1 over 2, because we're dealing with the case q equals to p, prime case. Assuming that f prime of x is not 0, or equivalently, you're not a p-th power, not every monomial is a p-th power, then the solutions to problem 2 are kind of nice. They're in fact product of 3 terms. One of them is a linear term, and the others are these binomials. And there's 2 additional parameters here. There's a sigma and a tau. And the sigma and a tau can vary. So sigma could be plus minus 1, and tau could be 0 and 1. Now, this is very nice because problem 2 was asking for a large collection of polynomials, and all of a sudden, there's only few of them, right? We can even write them down. But when Q is not prime, the solutions are much harder to describe. So if Q is a prime power, an arbitrary prime power, it's harder to describe the solutions. And in fact, the whole book, lacunary polynomials or finite fields, is almost entirely devoted to describing the solution to problem 2. And in his book, Reday actually completely characterizes solutions to the problem 2 in the case when Q is equal to P to the n, where P is bigger than 7, or n, the exponent, is at most 3. So he basically solves the problem in all cases, except for a very few cases when P is very small, or n is big, but P is small, right? So if you're willing to assume P is bigger than 7, then Reday has solved the problem. And even when P is small, like 2, 3, and 5, and 4 is also a prime power, Reday has also solved the problem when n is at most 3.
Oh, may I ask, I'm just curious, what is the main difficulty we meet in this case? I mean, when P is so small, say, the small case, what is the problem?
Yeah. That's a great question.
Yeah.
Unfortunately, I do not know where the bottleneck is. I do know the proof is hard even with this case, P bigger than 7. And yeah, and I actually so basically what you have to study is you have to continue this proof. So this proof, as you noticed here, we went on and showed that in the case when g of x is degree q plus 1 over 2, because we showed the lower bound, and we know also there's an upper bound, then f of x divides this polynomial, g of x plus x times g prime of x. Now, that's a very special condition. So what Reday does is he goes and so he looks at f of x. What is f of x? F of x is x to the q plus g of x, and analyzes when does that divide this polynomial. So then he has to compute this polynomial. And when you compute this product, there's a lot of relations that you get.
Yeah, right. Yeah.
And a lot of those and you basically want to force some of those coefficients to be 0 because f of x is lacunary. Right. And from these relations, he's able to deduce that, in fact, most of the other coefficients are 0. So there's not too many terms. That's sort of the idea. I actually do not know myself what happens when P is small. I have a feeling that it was resolved years later, but I don't know the reference. But I would guess that the problem is now solved even when P is 3, 2, 3, 4, and 5. But yes, but that's a good question. So if I just wanted to say one last thing about your question in case people are interested. So if you look at this reference I mentioned here in this paper, Tomasioni showcases what the solutions look like for problem 2. It is a bit of a large statement, but there's a discussion of that. It's just that in the case when Q is equal to P, the solution is quite nice. It's right here.
Yeah, I see. Okay, thank you.
No problem. So now let's turn to geometry. So we talked about algebra, and let's see where the geometry leads us. So in fact, Rede himself was interested in the following geometric problem. And here is the main geometric problem that Rede was interested in. It's a very natural problem to ask. So suppose you have a polynomial. So the question is about how many slopes are determined by a function. I mean, this is the kind of question that you can ask in a calculus class, with the only difference being in that in a calculus class, we work with real numbers. Here we're dealing with finite fields, but the question is just as natural. So here's what the question is. Suppose you have a polynomial f of x over a finite field fq in one variable. So the question is the following: how many different values does this difference quotient take as the values of a and b range over fq? So you have a and b. Okay, so assume a and b are not the same. A is not equal to b. Look at all possible quotients of this kind, f of b minus f of a divided by b minus a, and ask yourself, how many different quotients can you get? Now, of course, because we're dealing with a finite field, there's only finitely many possible quotients can we get. But can we show that there's a lot of these quotients somehow? That's sort of the question. What can we say about the size of the set? How many different quotients can we get? And geometrically, these are just slopes. We call these the slopes, right? The slopes of a secant line determined by the graph of a function. So this is a very natural problem to ask. And the problem can also be phrased as follows in the finite geometry language. Given a point set U of Q points, where Q again matches with the Q here, FQ, in the affine plane, AG2Q just stands for affine plane of dimension 2. So this is like the Euclidean plane, except over a finite field FQ. So given such a set of points, how many directions are determined by U? That's what we're really asking, because you can think of slopes as directions. And why did I say Q points? Well, that's because in this problem, I was looking at a graph of a function. And well, this is a graph of a function of one variable polynomial of fq. So if you try to plot the points, the number of x coordinates is just q, because you can plug in any fq point in the domain. And you get the corresponding y coordinate, which is the value of the function at that x coordinate. So it's clear that the graph of a function over a finite field, if you're just looking at fq points, it consists exactly of q points. So this is why these two questions are equivalent. Now, I want to describe in a bit more precise detail what do I mean by directions. So we should make it precise. And here's a precise definition. A direction is going to be denoted by parentheses and m. So a direction in the affine plane, AG2Q, which can be identified with just FQ square, is an element of the projective line. So it can be thought of an element of P1 FQ corresponding to the class of parallel lines with slope m. So you have all these parallel lines in the affine plane with slope m, and we imagine those parallel lines going off to infinity and meeting a point at infinity. This is how we projectivize the affine plane, by adding enough points at infinity. And all these parallel lines with slope m, they go meet together at the point at infinity m. And this point m, namely the parallel class, is called the direction, because literally it corresponds to the direction of every parallel line with this slope. Now, you may observe that P1 FQ actually has Q plus 1 distinct FQ points. So where is the Q plus 1th point? Well, it's the point at infinity. It's the slope infinity. It's the vertical direction, right? So you have y equals to mx plus b, where m can be any of the q values. M could vary. M could be a slope in FQ. That gives you q choices. But then there's also this one particular case when the line is a vertical line, and that's the infinity direction. So altogether, we have q plus 1 directions. And formally, we say that given a point set in the affine plane, AG2Q, we say that a direction is determined by U if there are 2 points in U, so that the line joining them has slope m. So this is a very intuitive definition. This is what it means for a direction to be determined by a point set. Just means that there's a line that is spanned by at least 2 points in the collection that gives you that slope. Okay, so now let's talk about a very important algebraic tool that Reday came up with. So Reday discovered a special polynomial which forms a bridge between the algebraic world of lacunary polynomials over finite fields and the geometric world of directions. So how do we connect the two worlds? So here was Reday's idea. We start with a point set U in the affine plane, given by, well, it's got how many points? Well, as many points as the cardinality of the set U. So I'm going to write those points as AI comma BI, as I goes from 1 to U. So this is the size of U. So that we can talk about what points live in U. So given such a description of the set U, we can define its Reday polynomial as follows. So this is a polynomial in 2 variables, x and y. And it's defined as follows. It's the product of all linear factors, x plus AI y minus bi, where I ranges from 1 up to the size, the cardinality of the set U. And this means that we know it's factorization, but oftentimes it's also helpful to expand this polynomial in this way so that it becomes a polynomial in the variable x, but with coefficients in the polynomial y, in the variable y. So usually we'll write it. Now, what is the advantage of writing it this way? Well, the advantage is that, well, first of all, we have some control over the degree. Notice that the total degree of the polynomial h of x is just u, size of u, because there's only size of u, cardinality u, many linear terms. So the maximum degree is cardinality of u. And the way I've indexed these coefficients is that forces degree of hj to be at most j. For example, degree of h1 is at most 1, so that the total degree is u, cardinality of u. And this will actually end up being quite useful for us later. And an important technique in the field of Reday polynomials is that once you can, first you consider this 2-variable polynomial, but then you make a choice of what y can be. And when you make a choice by specializing y to be, for example, some y0, some element in the field, and oftentimes when you look at the resulting 1-variable polynomial, this reveals some important information. And what does it reveal? Well, we're going to show that this can sometimes be a lacunary polynomial. Once we can show that you get a lacunary polynomial in 1 variable, then we can apply the earlier results and say something about that polynomial. Okay. So,
excuse me, but what does it mean specific choice? So you mean that
right.
Yeah, that is very important, right? Yeah, because
Yeah,
otherwise you never will get what you would like to get.
Yeah, so what we're going to show, that's a good question. So I guess here I'm just saying that the technique that's useful is we don't know how to deal with 2-variable polynomials. We don't have tools like understanding lacunary polynomials over a field with two variables. I don't think we have the theory for it yet, right? So Reday's theory is only about lacunary polynomials in one variable.
Yeah, right. Yeah.
And that's why we have to somehow specialize y. And I'm going to show you in the proof how to specialize this y.
Okay.
So that a lot of these coefficients become 0. So you get something lacunary. Yeah, so I'm gonna show you how to do that.
Okay.
So here we're gonna talk about the first kind of fundamental theorem in the theory of directions. And this theorem was the kind of the starting point of this research. This is a theorem that's attributed to Raday and Megiesi. And the theorem has intuitively makes a lot of sense. So let me try to build the intuition for it. So suppose we have P points in AG2P. So I want to emphasize that Raday-Megiesi theorem is only about, in its historical form, is only about the case when Q, the size of the finite field, is P, a prime. Okay, so suppose we have P points in AG2P. Then if all the points are on a line, then of course only one direction is determined because all the points are on a line. If any 2 points you take from that line, there's only one direction. So this is an extremal case where there are not that many directions. In fact, there's as little as possible direction, namely 1. But imagine that the points are not all on a line. In that case, we expect intuitively, there's many, many more directions that are determined by the set of points. And the following results by Raday and Megiesi, this takes this intuition and makes it quantitatively precise. And here's what the result says. Suppose P is a prime, and you take set of P points in AG2P. Then either those points form a line, or they determine at least P plus 3 over 2 directions. So again, this is in alignment with our intuition, because either you are a line, in which case you determine one direction, or the point set determines at least this many directions, P plus 3 over 2, which is a sizable quantity, right? This is basically half of the directions. It's more than half the directions, because remember, there's P plus 1 directions. And this says that more than half the directions are obtained. And I will mention that the value of P plus 3 over 2 is actually sharp. You can't necessarily do better than this. So there exists some configuration of P points that achieve exactly P plus 3 over 2 directions in AG2P when P is an odd prime. And I'm going to show you what that set is in the next few slides. There's going to be a slide which I'm going to show you a set of points, of P points, which determines exactly P plus 3 over 2 directions. So from that point of view, when P is prime, Raday's theorem is sharp. Raday-Megiesi's theorem is sharp. So let's try. We're gonna go through the proof of this theorem, because we have already developed the tools to prove this theorem. Okay. So the following lemma plays a central role in the proof of Raday-Megiesi's theorem. So here's what the lemma says. And this lemma actually works for any Q. Notice here I didn't write P prime. Here I wrote Q because the lemma actually holds more generally when you're working over a finite field of any cardinality, including prime powers. It does not have to be a prime. So suppose you take a set of points in AG2Q. Well, how many points? Well, you take Q points, same as the size of the field. And let me label those points as A1, B1, A2, B2, all the way until AQ, BQ. And we're going to let H, the polynomial H, to denote the reducible polynomial. So again, this is going to be a product of x plus AI y minus bi. I goes from 1 to q. And now I'm going to take a fixed direction, and I'm going to call that y0. Then here's the fundamental key lemma, that the direction is not determined by you if and only if h of x comma y0 is x to the q minus x. So it's very interesting. So when you pick a direction that is not determined by the point set, then when you specialize the reducible polynomial at that y0, now it becomes a polynomial of one variable. And what this theorem says is that it becomes this particular polynomial, x to the q minus x. Very interesting result. So here's the proof. So let me show you the forward direction, and then the backward direction is going to be the backward implication is going to be similar or basically the same. So let's try to assume that y0 is not determined by you, and let's try to prove that the reducible polynomial, when it's specialized to y0, is in fact equals to x to the q minus x. So let's assume that y0 is not determined by you. Then we're going to show that the q values that you get, namely ai y0 minus bi, for I that goes from 1 up to q, are in fact distinct. We're claiming that these are distinct values. Well, why is that? This is because assume to the contrary that the two values collided for some I and j. So ai y0 minus bi is equal to aj y0 minus bj for some I not equal to j. But then it's simple to solve for y from this equation, and we get that y0, it's simple to solve for y0 from that equation. We get that y0 is bi minus bj divided by ai minus aj. But then, by definition, we've realized y0 as a direction determined by the point set, because these are the points in the collection. And that's a contradiction because we have chosen y to be a direction not determined by you. So what did we show? We showed that these terms here are all distinct. So when you look at the reducible polynomial evaluated at y equals to y0, then all of these terms are distinct. These are distinct. And how many terms are there? There are q terms. So this polynomial, h of x comma y0, is a polynomial of degree q with distinct fq roots. But there's only one such polynomial. And that polynomial is x to the q minus x. And that proves the one direction. And the other direction is similar. So assuming that h to the q, assuming that h of x comma y0 is x to the q minus x, then working backwards, we see that h of x, y0 must have distinct roots because this polynomial has distinct roots. But if this has distinct roots, let's look at the definition of h of x, y. It follows that ai y0 minus bi is not equal to aj y0 minus bj for any I and j. And therefore, y0 is not determined by you. Because being determined by you means that you are a quotient of this kind. But being a quotient of this kind is equivalent to saying that ai y0 minus bi is equal to aj y0 minus bj. So that shows that the result is true, the lemma is true. Okay, so let's go on. So now we are ready to prove the Reday-Megiesi theorem. So our goal is to show that if you have a set of p points where p is prime, then either the set U determines a line, so all the points in U are in a line, or they determine at least p plus 3 over 2 distinct directions. So for technical reasons, what we need is that we want the infinity direction to be in the set D. And I'll say why. So this will become useful. This is not hard to achieve because what does it mean infinity is in D? It means the vertical direction is determined by D, but that's easy. So whatever your point set is, just rotate it so that the vertical line is determined by 2 points in your collection. Now, from the previous lemma, we know that the direction is not determined by you if and only if the Reday polynomial specialized at y0 is x to the p minus x. But since u is a set of size p, that means that my Reday polynomial looks like this. So Reday polynomial always has degree equals to the cardinality of the set. And we write it in this way where we decrease the powers of x one by one. And so last one is x to the power of 0, which is not present. And we increase the indices of h. So this is h1 of y, h2 of y, all the way until hp of y. With this convention, the degree of hj is at most j. And now here is the crucial observation. How many points are not determined by the set U? Well, let's think about it. D is the set of directions determined by the point set. And how many total directions are there? Well, there's p plus 1 total directions. So, and we're also assuming that infinity is in D. That means that the remaining directions, p plus 1 minus D, those are all elements of FQ. They can be identified by elements of FQ because they cannot be infinity direction. And well, there's total of p plus 1 directions. And by definition, there's this many directions not determined by U. But that means that HJY vanishes for at least p plus 1 minus D points. Because for each of those choices of y0, when you plug it in, you get that h of xy0 is x to the p minus x, which means all the intermediate coefficients vanish. So all of these h sub j y's, in fact, vanish for at least this many points. But now we use the fact that a polynomial of degree j cannot vanish at j plus 1 points. If a polynomial of degree j vanishes at j plus 1 or more points, it has to be identical to 0. So, well, what happens here? Well, this means that all the polynomials, all the polynomial coefficients here, like h1y, h2y, all the way until h p minus dy, they must be identical to 0 because their degrees are too small. Their degrees are at most p minus the size of d, and yet they vanish at p plus 1 minus d points. So by identity theorem for polynomials, they have to go away. They have to be 0. So notice here we're showing that the polynomial is lacunary. Lots of coefficients go away. So now that we know, I mean, here's the beauty of the argument. Now that we know these hi goes away, they go away. Now we're gonna specialize in a direction which is determined by the point set U. So just take any z, the direction determined by the point set, so z is in D, and then look at the specialized Reday polynomial. We want to reduce it to a one-variable polynomial, so we plug it in. Notice that in the Reday polynomial, after the leading term x to the p, the next non-zero term is the polynomial h sub p minus d plus 1. And then it's h sub p minus d plus 2, dot. It's increasing, right? This is the first non-zero one that could ever appear because all the other polynomials are identically 0. So h sub j for lower j are all gone. They're all 0. But this is great because now we have this polynomial which is of this type. What is the shape of this polynomial? So let me call this polynomial h sub zx because it's a polynomial of x, really, depending on the z. Z is just fixed direction. And we have written this polynomial in the following way. We've written it in the form x to the p plus gzx, where g of z has degree at most d minus 1, that's because if you look here, the polynomials in terms of x, the variable x, the powers of x are decreasing, and the biggest power of x is d minus 1. So degree of g of z is at most d minus 1. But this polynomial is fully reducible because the Reday polynomial itself was fully reducible. The way Reday polynomial was defined was like a product of linear factors. So if you specialize one of the variables, it's still a product of linear factors. So it's a fully reducible polynomial. And by Reday's theorem, it means that the second term, g sub z, must have degree at least p plus 1 over 2. So degree of g has to be at least p plus 1 over 2. But we just showed that d minus 1 is bigger than degree of g. So together, d minus 1 is bigger than the degree of g, and degree of g is bigger than p plus 1 over 2. That shows that d minus 1 has to be at least as big as p plus 1 over 2. And therefore, if you move 1 to the other side, we get the degree of d is bigger than or equal to p plus 3 over 2. And that's the proof of Reday-Meggiez's theorem. So it's a really nice proof because it showcases how you can use polynomials, in this case, Reday polynomial, to say something about geometry, namely the number of possible directions that you have. And the proof idea is not very complicated. I think that the difficult part is to put all of these together. Each individual piece is elementary, but realizing that this key lemma is the very clever part. That this lemma shows you that the polynomial, Reday polynomial, specializes to x to the q minus x for every point that is not determined, for every direction that's not determined by y, means that if your direction set were to be too small, then p plus 1 minus d would be too big, and there'd be too much vanishing. And somehow Reday's other theorem on fully reducible lacunary polynomials shows you that's not the case. So we have an interplay between too many coefficients vanishing and too few of directions determined. So we want, since we can't have too many coefficients vanishing, we should have enough directions. That's basically the idea. So that's the proof, and we're going to move on to a result by Blokhuis and Shriver. So Blokhuis and Shriver actually gave a different proof of Reday's theorem. So they gave a different proof of Reday-Meggiez's theorem. They gave a different proof of this theorem using the polynomial method. But they also showed something stronger. So basically, they showed that if you have a set of p points in AG2P where p is prime, then the set determines exactly p plus 3 over 2 directions, not points, it should directions here. It determines exactly p plus 3 over 2 directions if and only if u is projectively the equivalent to this set. So notice that this set has exactly p elements because this has p minus 1 over 2 elements. This has p minus 1 over 2 elements. That's together of p minus 1 elements. And then there's one more element here. So there's together p elements. So these sets are very special because they determine exactly p plus 3 over 2 directions. And they showed that these are the only ones. Right. So Reday-Meggiez's theorem is sharp, and Blokhuis and Shriver were able to find the threshold case. These are the special sets where the number of directions is, in fact, is given by the minimum of p plus 3 over 2. And then there was this development by Gotch. Gotch showed in 2003 something even stronger, that suppose p is a prime, then any set of p points in AG2P is either a line or a set mentioned in the Blokhuis-Shriver theorem, namely this set, or it determines at least 2 times p plus 2 over 3 directions. So this is a stronger result, much stronger, because the Reday-Meghezi theorem was about roughly 50% of the directions is determined by the point set. But Gauch's theorem shows that it determines at least roughly 66% of the directions, provided that the points are not on a line and provided that it avoids this particular exceptional set that's in the Lovász-Schreiber theorem. So basically, if you are a line, then it determines one direction. If you are this set, or if you're a set that's projectively equivalent to this set, then the set determines exactly p plus 3 over 2 directions. And if you're not projectively equivalent to this, then the set determines at least 2 times p plus 2 over 3 directions. And all of this is for the case when the finite field has prime cardinality, q is equal to p. And here are the results. So the Lovász and Schreiber result from 1981, and the Gauch's result is from 2003. Now, what about the case when q is not a prime? So what happens when q is an arbitrary prime? So Simeon Ball proved the following pretty incredible result. This is going to hold for all prime powers. And let me mention that a lot of this work was also built on previous work by Reday, namely the work that we've discussed, but also on the joint work that Ball himself did with Blokhuis, Brouwer, Storm, and Saunier. I'm going to give references at the end of this slide. So here's what the theorem says. So instead of talking about point sets containing q points, I phrased the theorem in terms of functions, graph of a function. It's equivalent because having q points is basically, after rotation, is equivalent to having a graph of a function defined over fq. And the theorem is quite nice. So let f be any function such that f of 0 is 0 and q is any odd prime power. Then let n be the number of directions determined by the graph of f. So this is the directions that we want to bound. Then n is at least as big as q plus 3 over 2. This is Reday-Meghezi bound. Or there is a subfield k of fq such that the graph is k linear. So this clause doesn't apply in Reday-Meghezi theorem, because in Reday-Meghezi theorem, you're dealing with fp where p is prime, and fp doesn't have any proper subfields. Fp is its prime subfield itself, so there's nothing smaller than fp. But you see, when you're dealing with fq where q is a prime power, then there's all these subfields that are hiding inside fq, and this kind of phenomena is called subfield obstruction. So basically, this part of the theorem shows that either the number of directions is at least as big as q plus 3 over 2, which is what you predicted from Reday-Meghezi theorem, or that there's a reason coming from a subfield obstruction that limits the number of directions, and that's because the graph is k-linear. It's not necessarily fq linear, because if the graph was fq linear, then it will only determine one direction. But it's possible that the graph is linear over some smaller field. And then in the case when the graph of a function is, in fact, linear, the function is linear over a smaller subfield, then we have the following refinement. If k is the largest subfield over which the graph is k-linear, then we can say that the number of directions, it's still as big as q divided by size of the field k plus 1. So basically, imagine the case when k is not so big. So k is a small subfield, then this quantity gets bigger. So, which makes sense. Somehow when K gets larger, so the subfield gets closer and closer to the big field, FQ, then of course, if K gets very, very large, then this quantity gets tiny, and the number of directions reduce, right? So linear things have less directions. That's the intuition. And here are the two references for these results. So Simeon-Boll's result is called the number of directions determined by a function over a finite field. And it's from the Journal of Combinatorial Theory, Series A from 2003. And then it was built on some of his work, some of Boll's work with the other authors, Blokhuis, Brouwer, Storm, and Sonyi, from an earlier 1999 paper. So last thing I wanted to mention is Sonyi's extension. Elena, I just wanted to ask to see if I can still continue or if I should stop because it's already 11:06.
Well, up to you because you can.
Online.
Yeah,
right.
yeah.
I'm happy to finish the slides if you want, but I'm also happy to stop wherever you prefer. So I have about, you can see it's 70 out of 89, so I have about 20 more clicks.
Yeah.
So maybe I can finish the slides, or I can also continue next. Yeah, so I'm happy to continue. Okay. So last thing I wanted to mention is the Sonyi's extension of Raday's theorem. So far we've looked at the number of directions determined by Q points. But what happens when you look at a set consisting of fewer than Q points? And basically, there's the result. If you have a point set in AG2Q such that the number of points is not necessarily Q, but it's pretty close to Q. So it's at most Q, but bigger than Q minus root Q over 2. Then one of the following two statements must hold. Either U itself determines at least Q plus 1 over 2 directions, which is pretty good because it determines a lot of directions, or you can extend U to a bigger set that contains Q points, and yet that has the same direction set as U. And this is neat because it allows you to go to the other theorem. The other theorem was about the case when the point set had Q points, right? But it's unclear that you can extend the set and retain the same directions. That's unclear. And Sonyi showed this is possible. So either you have enough directions or you can extend. And this was from a 1996 result of Sonyi. And the proof idea can be summarized in the following 4 bullet points. First, given a point set U with n points, we again label the points of U in this way, AI, BI, where I is between 1 and n. Then let D denote the set of directions of U as before. And as before, we have the Raday polynomial, which is a product of linear factors, x plus AI y minus BI. And again, for each fixed y, we have this specialized Raday polynomial, which you think of it as a polynomial in one variable, x. And then we also saw the following, that if you look at this set, for each fixed y, we can look at these combinations, AIY minus BI, or if you like, minus AIY plus BI, that's equivalent. Then we saw that HYX divides x to the Q minus x. Basically, we saw this if and only if AY consists of distinct elements. And if and only if Y is not in the direction set. If and only Y is not in the direction set. And so the idea is that if you look at the quotient x to the Q minus x divided by HYX, then this is a polynomial which vanishes at every point of the complementary set. And that's because HYX divides x to the Q minus x. So you can look at the ratio. The ratio is a polynomial. And it is going to vanish elsewhere, away from A of y, by definition, because HYX vanishes at these points because of its definition. These are the roots of HY of x. And but what does it mean for a polynomial to vanish at every point? That means that if you write down the roots, then the coefficients are going to be symmetric polynomials in the roots. So the coefficients of this this ratio. This looks like a quotient, but really it's a polynomial. It's like the residual part. And now this is going to be symmetric in the roots. So it's a symmetric polynomial in the roots. And the roots are ay bar, what I call ay bar. And more precisely, you can write it like this. So recall that sigma k is the elementary symmetric function, kth elementary symmetric function. So that means that if you look at this quotient, which I'm going to call f of x comma y, well, it's a polynomial which vanishes exactly at every point of this set ay bar. So its coefficients are symmetric polynomials in ay bar. And because f of xy is this quotient, h of xy times f of xy is equal to x to the q minus x. But the tricky thing is this is only true. This is not literally true as polynomials, but it's only true for y not in D. And this is because it doesn't really make sense to talk about f of xy as a polynomial, because how are we going to make sense of the symmetric polynomial of a of y? This only makes sense for fixed y. For a fixed y, this concept makes sense because a of y makes sense for a fixed y. And so it's a bit of a subtle notational thing, but this holds for each y not in D. And then the proof of Szonyi's extension is that we take a set U, which has size n, and n is sandwiched between q and q minus root q over 2. Then I look at m. So what is m? M is q minus n. That's the complementary degree. That's the degree of f. All right, that's because this is total degree q. This is degree n, because that's degree n. That's the size of u. This means that f must have degree q minus n. F has degree m. And using the notation from the previous slide, we know that this factors into distinct linear factors for each fixed y. And this follows from the fact that this identity holds. And for each y not in D, but x to the q minus x has distinct roots. So of course, this must also have distinct roots. It's a factor of something that has distinct roots. So it follows that because this is true for every y not in D, and you have as many as q plus 1 minus D choices for y, so the number of directions is D. So the number of points that are not directions is q plus 1 minus D. And each of them has exactly m roots. That means that f has a lot of roots. It has at least q plus 1 minus D times m distinct roots. But you can say something more if you take any irreducible, if you take any factor of f. So for example, if you take any psi of xy, then this also has a lot of roots, simply because f of x has distinct roots. And you say the same argument, you use the same argument to see that it has a lot of roots. And so, final slide, if the direction set has at least q plus 1 over 2 choices, we're done. Because that was the first clause of Szonyi's. Otherwise, assume that it has less than q plus 1 over 2 directions. Then you look at this element, q plus 1, you look at the size of q plus 1 minus D. Well, clearly it's bigger than q plus 1 over 2 because D is less than q plus 1 over 2. And then each psi of x has more than q plus 1 over 2 times D fq rational points from the previous slide, where D is the degree of psi of x. Now, if psi of x were actually an irreducible curve, if it defined an irreducible curve, then we know from the Hasse-Weil bound that the number of points on a degree D irreducible curve is at most q plus 1 plus the genus times root q, and the genus of a degree D plane curve is d minus 1 times d minus 2 over 2. So we get that it can have at most this many points. But then you get a contradiction because you have that it has more than this many points, but it's less than this many points. This is not really possible unless D is 1. Because notice if D gets larger, this is bigger than this. This is square root. This is gross square root of q, but this is linear in q with coefficient D bigger than So then there's a contradiction unless d is equal to 1. So what's the conclusion? The conclusion is that every irreducible factor must in fact have degree 1, because d was the degree of an irreducible factor of f. That means that f of xy in fact factors into distinct linear factors. And therefore we get that f of xy is a product of linear factors like this. And the last step, which I don't have time to explain, is that we add these new points, these ci bi's. This should be di, sorry. Ci di's, this should be a di here. We add these points to U to get a larger set. And that set contains U, and it turns out that they have the same directions as U. And that's all I have. And I apologize for some of the typos. I'm going to fix them. I just noticed that there's a small typo here. This 2 shouldn't be here.
Everything is fine. Well, actually, I really like this bridging between the algebraic approach of polynomials and geometrical ones of directions.
Yeah,
so it
good.
seems to me that next time you are going to show us what is exactly the bridge between this theory and some theoretical theory, right?
Yes. Clique number with the Paley graph.
Clique number, yes, that is amazing.
Yeah.
Yes, it's really amazing. Okay, Shamil, thank you so much. I really appreciate your time and this explanation. Actually, great explanation. So
thank you so much.
Yes, today I understood a lot about direction. So in 2 weeks, I hope to get something new about this bridge between two theories. Yeah, okay, thank you so much.
Thank you. Yeah, and I will send you the slides. I will send you the slides for the.
Yeah, sure. Yeah, please. Yeah, thank you.
After I come back. Yeah. Take care. Bye, Elena. Bye.
Yeah, bye.